So welcome everybody to another presentation in the Language Technology and Data Analysis Laboratory Webinar Series 2021. Before we start, I'd like to acknowledge the country. So the University of Queensland, which sponsors LADAL and which is hosting LADAL, acknowledge the traditional owners and their custodianship of the lands on which we meet. We would like to pay our respects to their ancestors and the descendants who continue cultural and spiritual connections to country. And we recognize their valuable contributions to Australian and global society. If you'd like to know more about the Language Technology and Data Analysis Lab, LADAL, you can visit our homepage, or you can also check out more information about the current and upcoming as well as past presentations on the LADAL Opening Webinar Series website. You can follow us on Twitter to get notifications of upcoming talks and events. And you can also contact us via email using the handle that you see there. It's a real pleasure to introduce today's speakers, Ben Foley and Janet Wiles. Ben is the project manager of the Transcription Acceleration Project, TAP, at the Center of Excellence for the Dynamics of Language, CODL. A major focus of TAP is the development of user-friendly speech recognition tools, which is also topic of today's presentation. In addition, Ben has created several apps and websites documenting and making first languages accessible to the wider public. So he's wandering the worlds between language documentation and language technology. Very, very interesting. Janet Wiles. Janet is Professor of Human-Centered Computing Discipline at the University of Queensland and leads the Future Technology thread of CODL. She has 30 years experience in cross-disciplinary research and teaching, including artificial intelligence, language technologies, and social robotics, leading teams that span engineering, humanities, social sciences, and neuroscience. So I welcome today's speakers, and I'm very much looking forward to their fantastic presentation. I'll stop sharing now, and I want to welcome Janet and Ben.
Thanks, Martin.
Okay, so thank you. Our topic is semi-automated speech recognition using Elpis. And I was just going to start by saying a little bit about what human-centered computing is. So the human-centered computing discipline at the University of Queensland is a group of researchers, cross-disciplinary researchers, who research how to design and create technologies that empower people and their communities. And so it's not the technology itself, but the fact that the technology is usable that is really the metrics we're looking for. And so we, the approach we use takes the context of use, understanding particularly people's lived experience. Our projects vary across a very broad range of areas. This is from our website if you're interested in drilling down into any of our projects further. And so a large part of the language technologies work we do is with the ARC Centre of Excellence, with the Technology Centre of Excellence for the Dynamics of Language, CODL. So the community itself comes from design, robotics, engineering, and computer science. And we work with a lot of different disciplines across the humanities, the social sciences, behavioral sciences, and also engineering. So one of the things that we're looking for is really not designing for various applications, but designing with communities. And so the title of our talk, Semi-Automated, there's a reason why it's semi rather than fully automated. And hopefully as Ben goes through the details of Elpis, you'll get a sense of why that is. Ben, over to you.
Thanks, Janet. So let's see how this has played out in one of the projects that we've been working on in the Transcription Acceleration Project at CODL. And it's a co-design project looking at developing language technologies with linguists and language workers. Now, this one that we'll be looking at today, Elpis, is a tool that uses speech recognition technology. So the crux of this is to make the process of transcribing easier. And so not fully automating it, but to allow the technology to make the person's tasks easier or richer, or to allow the person who's doing the transcribing to focus on different aspects of that. So many of us linguists, language workers, are familiar with transcribing. Within CODAL, the last time we checked, there were over 50 fieldwork members transcribing and documenting languages over 70 locations around Australia and globally, and working with over 120 languages. So here we see some photos of different ways that language documentation and transcription can happen. So it often happens in communities, it sometimes happens in offices, in schools, it sometimes happens when we're sitting around on the deck of someone's house. There's usually a computer or a video camera or an audio recorder involved these days. But at some level, there's speech or sign or a communicative gesture happening that's being documented. And then the process of annotating that, the transcribing, is being performed for various reasons, whether it's to create resources for language learning or to assist the researchers with the language research that they're doing. Now, this is a familiar tool for some of us. You might recognize this interface. This is a computer program called ELAN, and this is a popular, well, common program that is used quite broadly and widely in the language documentation field for annotating speech, video, media. There are lots of other interfaces that people use. However it's done, it tends to be a slow process. So some years ago, a transcription survey of linguists within the group found that on average, it took people 40 minutes to transcribe 1 minute of audio. For some people, it was longer, 250 minutes, and for some people, it was shorter. It depended on the fluency of the person doing the transcription, depended on the quality of the recordings. But however it happened, it tended to be quite a slow process. So as we can document languages more readily these days with digital recording tools, so speech audio recorders or video cameras, we can amass quantities of material, quantities of recording. This transcription bottleneck really hinders the process of doing further analysis or adaptation of those materials into other formats. Some years ago, at a language technology workshop, somebody asked, does anyone who knows anything about speech recognition? Can speech recognition help us working in this language documentation field, and particularly with endangered languages or languages with smaller quantities of recorded material? Can technology help us with the language work? Well, one thing led to another, and we started to work with some speech recognition, some experts in speech recognition tech. So I'll get to that in a moment. There are 7,000 plus living languages in the world, 8,500 by some counts. About half of these have some sort of written tradition, possibly more. For a lot of these, it's only quite recently that this written tradition of the language has evolved. This diagram shows that language technologies are not equally covered across all of the languages in the world. So while 3,000 might have a written tradition, and most of these are supported by international standards of writing, of symbols, by this system called Unicode. And for almost all of these, the writing of the language can be supported in a digital format by fonts. fewer languages have access to the input mechanisms of smartphone keyboards. So around 1,000 languages now have keyboards that the language communities can input their communication into devices. So this is interesting that of these 900+ languages, this covers about 95% of the world's population in their first language. So there's quite a good coverage of population being able to input their language into the digital devices. As we get to these speech recognition and text-to-speech technologies, we see fewer languages supported by organizations and companies like Google, Microsoft, these big providers of existing systems. And then in the clouds above those, even fewer languages are supported in language technologies like search engines and machine translation systems. This list comes from Little's paper about Indigenous language technologies in Canada. It's well worth looking at for an assessment of the availability and the complexity of language technologies and the relationship of the quantities of data that are required for language technologies for communities to access technologies for these different processes. So for a language community, the most accessible technology is a keyboard in the language. It requires a small quantity of data and not particularly sophisticated software skills to set them up. You can download tools from a few providers to build a keyboard in a language without much material required to start that off. As we go further down in the list, we see tools like spell checking requiring more language data to set the tool up for the community. So fewer communities will have access to these. Language technologies like speech recognition and machine translation are very complex, and they might require sophisticated computational software skills to install them or to run them, and they typically require loads of data to use them. And so for the endangered language communities around the world, these have typically been out of reach. In this talk, we're looking at speech recognition, but these concerns also will apply to these other technologies like translation. And so we'll look at speech recognition in the context of the design of a technology which makes speech recognition more accessible for language communities. So speech recognition, for the most part, has been a solved problem from a computer science point of view, at least for the last 15 years. So there are speech recognition technologies which work extremely well for languages like English, Russian, Portuguese, Spanish, languages that have large quantities of data. And these have been around for at least 10, 15 years. So this is not necessarily cutting edge research that we're talking about. However, the application of these for the rest of the world's languages still is. So speech recognition is this, the traditional speech recognition approach is to develop different models of different parts of language, and then to build a system that you can put untranscribed audio into and obtain a hypothesis or a machine transcription, a best guess at what that untranscribed audio was saying. So the components are an acoustic model, a lexicon, and a language model. The acoustic model is how the system learns about the sounds in the language and the relationship to the phonemes. The lexicon is the sequence of phonemes and how they create words. The language model is about disambiguating words and learning about sequences of words that make utterances. So in the example here, we have the word your. The acoustic model learns that the sound your is written as such in the blue box. The lexical model learns that there might be a few different ways of writing this sound, your. And the language model learns that there might be a few different ways that this word your can occur in sentences, and the likelihood of a particular word, your, as in you are, your possessive, or your, as in old story book. The tool that we're talking about, Elpis, started a few years ago in a workshop with more than 20 software engineers. It took us 2.5 days to install this tool called Caldi, which is this quite sophisticated and well-established speech recognition toolkit. Very powerful tool, very difficult to run. Even for people with experience in the field, it still took 2.5 days to get this thing going. We were doing this in the context of wanting to demonstrate how it might be useful for a language with limited resources. And it was quite dispiriting to get to the beginning of the second day and still have it not running when we knew that we were going to present it, or we were intending to present our results on the end of the third day. We got there in the end, but it was quite a learning curve. The first version of Elpis looked like this. So although we were able to get some results out of it, it was still quite daunting for someone who wasn't a computer scientist to use. Seeing this text scrolling past really fast as the thing trained was quite frightening. And the feedback that it gave was obtuse. Even here, we see that the feedback it gives in the middle of the screen, warning, you have only one speaker. This is probably a bad idea. So these kind of messages that the software was giving back were not particularly encouraging, quite scary. And we knew that that was a problem. So over a summer program at the University of Queensland, we developed a graphical user interface. So a piece of software, a kind of web-looking thing that people could use to interact with the program that was running in the background. So this was developed in a co-design or a human-centered computing kind of participatory design approach, where rather than us thinking that we knew best, we sat with linguists for a week and language workers, and we looked at the ways that people were currently doing transcription, and we collaboratively and iteratively designed this tool in a way that was going to work with people's existing workflows rather than us kind of parachuting in a new workflow and a new tool for people to learn. So on this slide, we see some of the stages of the co-design process. Here's a traditional sort of user experience design topics. There were processes of reflection upon the current ways of doing things, lots of discussion about how things were done and how things might be, how work processes might change. Rather than going straight into building a tool, we spent some weeks drawing up how this thing might look like and how this thing might work on paper, because it's a lot cheaper to draw things on paper rather than spending a week building something in code and then finding that it doesn't work. And so through this process, working with the users, the intended users of the program, we developed this first user interface. So here we've gone from the screen of text that you interact with by typing instructions into a command line to a wizard style interface that you can operate by clicking buttons and dragging and dropping files, much more aligned with the way that people expect computer programs to work, particularly if people don't come from a software engineering background or a speech science background. Some of the technologies that are involved in this process, so Elpis wraps existing technologies. So we haven't written speech recognition engines from scratch. We're wrapping existing tools. So we began with the Caldi speech recognition toolkit, and we now also include ESPNET and Hugging Face Transformers WAV2Vec2, which I'll talk about more later on in the presentation. So the process of using Elpis, the right-hand diagram, we input audio and LAN files. These are resampled and the formats are converted, and some processes happen whereby the annotation has sort of cleaned, some punctuation rules are affected to strip out tokens that might confuse the speech recognition system, and some assets that a word list is generated and pronunciation dictionary is generated. This is then used to train the model. Once the model's been trained, raw untranscribed audio can be input, and then an inference transcription is generated in the ELAN format. So the ELAN input and the ELAN output, we also originally started with a PRAT text grid format and plain text input formats. Elpis also has an engine in it which can receive different language data formats. So the input and the output formats being ELAN was primarily designed based on the input of the co-design process. So I'll talk now a little about the process of file preparation. What is required to get the data ready to work with this system? So we do need a corpus. We do need some training data to set the system up with. And this is in the format of matching transcriptions and audio files. So these can either be phonemically transcribed or they can be word transcribed. The word level transcription doesn't have to be word for word. It can be in this sentence or utterance length. So these are the sorts of formats that people are typically already doing. So we're not expecting people to retranscribe their corpora to get it into a machine-ready format. We're looking at supporting existing formats. One thing that does make a difference is to not include speaker and language codes in the transcription. So this is something that a lot of linguists do, is by typing the speaker code. So in this top example, the DVE, Dan Benesh, NLD would be the language code, although that's actually not in Dutch. So this is a typical practice of many linguists, is to type these codes into the transcriptions. So for machine learning, or machine use of this language data, it's best if those transcriptions don't have those in there. Now, again, we don't expect that the users would go through and laboriously take those out to be able to use the material in the system. So we have a process whereby those things can be automatically stripped out. Another good practice is to separate different speakers onto separate tiers in ELAN. And that gives the system an opportunity to learn that the sounds that one person is making are different from the sounds that another person is making, and accommodate those. So again, in the second example here, you can see that the speaker code with the colon has been shifted out. So rather than being included in the annotation, it's still in the metadata of the file, but perhaps has a tier attribute or by some other method, depending on the functions of the transcription tool that has been used to create the corpus. So once the corpus has been sort of prepared, the files have been selected to use, then the user generates a mapping of the letters in the orthography to some symbol that represents how that cluster of letters is pronounced. So we can see how this is used in the system. The rules on the left are passed through the cleaned corpus. And for the words in the cleaned corpus, a fairly simple substitution happens where each character in the map is replaced with the code or the symbol that represents how that character is spoken. And so this is done so that the user can look through this pronunciation lexicon and see whether the representation of this word is adequately suggests how the word is spoken. And so when the machine sees this, it will be able to associate that section of audio with this sequence of pronunciation symbols. So this is a process or a stage in the process in which the human intervention is significant. So we're talking about semi-automated speech recognition. This is a point at which the person with the language knowledge can intervene and correct the automatic process. Something else that we see in this stage is that quite often the annotations might include things that are not literally what's being said, but are descriptive of what's happening in the audio sequence or in the audio signal. And so these descriptions of what is being spoken or what's happening, people laughing, people talking, car driving past, these sometimes end up in the annotations, and for the purposes of speech recognition need to be taken out, because the system might hear that ha 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 and try to associate that sound sequence with the words people laughing and get very confused. So I won't go through the process of using Elpis. If you're interested, there's a link here which has a sequence. It's a workshop guide which can take you through the process of installing it and stepping through the process of building up the data sets, creating the word lists, building the pronunciation lexicon, and then going through the training process and using the trained model to generate a new transcription. I'm just showing again here the interface, just a reminder of how kind of friendly it is, although it also does reveal some of what's happening behind the scenes, so that if you, as a non-computer scientist or a non-software engineer, happen to be working with it in collaboration with a person from Elpis crew or some other speech scientist, then this peek into the back end can be helpful into seeing what's going on behind the scenes. So the logs or the output of the speech recognition engine are being piped through into the interface. Now this came out of the co-design process where the original version didn't have any of this, and it just sat there with a little spinning icon for, depending on how long the training session would go for, maybe an hour, maybe 6 hours, maybe 9 days, depending on how much language data was being used to train the thing. And so bringing the information about what's happening in the background through into the interface was included to help with that feeling that, yes, something's happening. It's not just spinning its wheels. It hasn't crashed in the background. Things are still going on. And although some aspects of the text that's coming through is complete gibberish, it still gives us that indication that things are proceeding. So the other thing about Elpis is that it exposes only minimal settings. Speech recognition technologies tend to have hundreds or thousands of parameters which can be tweaked for different languages. And rather than exposing all of those, or rather than giving options for all of those in the interface, which would have been overwhelming to anybody, we've selected just a few of the settings that will have the most impact. Now, under the hood, what is speech recognition doing? So in the training process, the system is learning this association of the speech signal, the audio, to these symbols of pronunciation. So this is the acoustic model. Then it builds up a knowledge of the sequences of phones that make up words. This is the lexical model. And then it looks across all of the corpus text and learns from the sequences of words language model. Then when we put some audio that is untranscribed in to gain an inference, the system listens to the sounds in the new audio and matches them against sounds in the acoustic model. Words are then hypothesized based on likely sequences of the phonemes. And then it hypothesizes this most likely sequence of words based on this probabilities of which words following another word. So this diagram here shows, for the Abui language, some some options for hypothesis for a short utterance. So we can read this from left to right, and the ideal, or its best guess, is indicated by the sequence of words in between the lowest number circles, these states. So this first cluster at the beginning, there's a lot of options there. So we know that the machine's a little bit confused at the beginning, but then it sorts itself out a bit. And in the middle section, there are fewer options. It seems to know a little bit better what's going on here. So one example here is Muye Hepakai Dena Botol Homi Hekai. So following this pathway through this lattice gives us this suggested sentence, this utterance. But we can see that it has also these other options. And as a language expert, it can be really interesting to see what some of these other options might be. And it might be that some of these are actually more correct than the one that the machine suggests. So this, looking at the lattice or looking at what's happening under the hood, can tell us a little bit about the language. It certainly tells us a lot about what the machine thinks about the language. And we can use this to fine-tune the system by feeding in more examples of the words or the sounds where there is confusion. So if we were to wanted to improve the accuracy of this utterance, we would give more examples of this hekai, kaya, yari sort of sound, and then that would give the machine a better chance of working out what's actually going on in that little sequence. So what sort of results can we expect to gain from this, given that we're working with languages that, or experiments or research that tend to have small quantities of data? So the systems that Google and Microsoft have, the speech recognition technologies that we use in our phones, like Siri and Alexa, are typically trained on hundreds to thousands of hours of transcribed recordings. Now, this kind of quantity of data is typically inaccessible for any of the people that I've worked with over the years. And so we're interested to see what kind of results we can get if we work with, say, 1 hour or 10 hours of transcribed recordings. So the examples of the results that we can see on the screen here in the 2 sentences below is from some work with Zara Maxwell-Smith, where she trained a system on 1 hour of audio that was recorded in a classroom of a teacher, of an Indonesian language teacher. And we can see that the words in bold are the words that it has gotten wrong. The words not in bold, the bottom row here, is where Elpis has got things right. And it's interesting to see in the hypothesis that although we have these words that are considered to be wrong because they're not actually, the whole word is wrong, there's some syllabification splitting here, which is quite close to what the intended word, so menterjemahkan, part of that word has been correctly identified, and maybe even the beginning of that is pretty close, but then it's got these syllable splits in it, which technically cause that to be an error. And dictator is a word that is probably an English word that's being spoken in the Indonesian, with the Indonesian voicing. So this is an interesting error as well. But so with these results, Zara says the transcriptions are never perfect, but they're a good place to start from. And you can make corrections to those transcripts and feed them back in and train an improved model for the next round. So Zara's paper here has some really fabulous insights into what some of these errors, or how some of these errors come about and what might be done about them. Here's another example of a NASSAN, a very, very small model that we trained with NASSAN. And the results here, the manual transcription on the top row and the Elpis transcription on the bottom row. So here we kept that file out with the manual transcription, and we can make the comparison with it. And this top experiment was extraordinarily accurate. So the reason for this is that the training data that was given to the system was highly repetitive. So the machine had a lot of opportunities to learn these different ways that these words were spoken. Compare that with another NASSAN experiment, similar quantity of data, and a really quite unusable output, where it's only gotten one word of those utterances, of that utterance correct. Now, the reason why this performed poorly was that within that small quantity of data, there were multiple speakers and there were multiple languages. So the machine just didn't have a chance of learning anything significant about that language. So human in the loop. In these examples, we've seen people training a system and use it to transcribe some audio, edit and retrain. So it's a cyclical process where we build up a small system, edit, and either use that edited output in our research or feed that back into the machine and retrain. So the system can be slowly kind of retaught. Some quotes here from Oliver Adams, who has been doing some fabulous research in this area over the years. The takeaway here is that these recognition tools can be a canvas for correction and linguistic analysis. So the idea is not that we automate the transcription wholly and allow the researcher to go on to other things, but to maybe take away some of the pain points or the drudgery of the slog of the transcription process, and allow the linguist to spend time thinking about the language rather than and looking at the first transcription, making corrections rather than writing that transcription from scratch. So within Elpis at the moment, we have 3 speech recognition engines. One of them's still a work in process. The first and the oldest one that we have, this is CalDi. This is the machine, the speech recognition system that we began with. CalDi itself is a toolkit which has been around for 15 years or so, and it includes many different speech recognition recipes, from some fairly basic systems to some much more sophisticated artificial intelligence, kind of deep learning neural net techniques. The system that we've used, or the recipe that we've used from CalDi, and a recipe is a bit of jargon which refers to a process of data preparation and getting the files set up in a particular way, and then doing training based on a particular kind of setup of certain scripts. This recipe that we've used is the HMM-GMM technique, and it was selected because it's good for small data sets. Typically, if you've got less than 100 hours of training data, you won't see much benefit from using the more sophisticated neural network methods compared to a HMM-GMM. The other benefit is that it requires less computational resources. So I can run the CalDi speech recognition system on the laptop that I'm presenting from, where I wouldn't be able to do that with some of the other systems that we're using. So that means that it's something that I can take with me when I go to the field. So potentially do speech recognition training when I'm in a field documentation situation. And this is particularly important for languages that require the language recordings not to be shared with cloud providers or to be uploaded to servers, or that they need to stay in a community. Again, this is a point that came out of that co-design process, where rather than going for the computationally more efficient process of insisting that everyone uploads their files to a server, it was designed explicitly to be able to run locally based on the user's needs. The 2 other systems that we have in Elpis are ESPNET and Hugging Face's implementation of Wave2Vec 2. So these are both neural network speech recognition systems, both released only in the last few years. They're much more modern. And rather than building up these probabilistic understandings of language, they have a direct prediction of the tokens, so whether it's the words or the phones in the language based on the sounds. So they don't need a pronunciation lexicon, so they can skip over that whole process of generating the orthography and the pronunciation mapping and the correction of that. They don't need language models. And they work pretty well with as little as an hour of transcribed speech, depending on the complexities of that speech. So an hour of transcribed single speaker recordings will give reasonable results with these systems. However, they can't run on a laptop. They do need to run on a server. They use phenomenal amounts of computer power. And so these are limitations on their application. There's some links here for more information about them. But I thought it'd be interesting just to skip to some results from a recent experiment that Cecile has done with this language. And we can see here that, again, we're using this format where the human transcription's at the top and the machine hypothesis is the second row, that this system has given extraordinarily good results with only a few characters wrong in those utterances. So Wave2Vec 2 is what we call a transfer learning approach, where there's an existing acoustic model that has been pre-trained on 56,000 hours of speech. And so this is a great conglomeration of various languages. There's some English, there's Dutch, there's French, German, there's some Chinese, there's Japanese, there's Tamil, there's Bengali, there's multiple languages. It must be, there's about, I think, 50 odd languages in there. And then this enormous acoustic model is fine-tuned to the target language. So in this experiment, Cecile used, I think it was about 10 hours of transcribed material to fine-tune. And from that, she has this very low error rate. And when this was passed back to the linguist to check the results, it took the linguist less than 3 minutes to correct these 15 sentences. So across the 15 sentences, we can see that, whoops, sorry. Across the 15 sentences, we can see that there are very few mistakes, and they tend to be just a mix, some missed characters. For the most part, it has correctly identified complete utterances. It's really quite extraordinary results. So it seems that this speech recognition interface for assisting linguists in the way that they work with annotations, with transcriptions, seems to be working. And so it leads us to ask how this might happen, or how this approach might also benefit other technologies. Maybe one of the biggest takeaways is that the participatory co-design process has been the most beneficial. We've seen other graphical interfaces developed for some of these technologies along the way that didn't follow this co-design process, and they floundered because the designers or the developers had particular ideas about how things might work, but without doing those with the users, they got themselves into some extraordinary problems, which caused them technologies to be completely useless. The paper that's linked at the bottom here points out some other suggestions for future directions in language tech. And some of the most exciting might be that while we're doing all of this processing of the language data, there's a lot of information about the language recordings happening, going on under the hood, that could lead to some really fabulous analytics and visualizations. So this might lead to more understanding of the data, and to be able to see the language data in different ways could lead to new research insights into the languages. So this is an area that we're just starting to get into with Elpis, of enriching the process with some visualizations of what's happening along the way. And some really nice work was done on a thesis project last year that we're hoping to integrate into Elpis in the next little while. So visualizations of things like the word sequences, frequency ranking, vocab. But again, these are potentially beneficial if we work with the users, rather than just thinking of something, of generating graphs that look cool to a developer. There's really no point doing those if they're not actually useful for the researcher or the user. So in conclusion, language technologies, these semi-automated speech recognition tools can help fieldwork linguists, language documentation linguists, and language workers in other domains. And relatively small data sets, and these days very small data sets of an hour of annotated transcriptions, can give useful results. The biggest challenge is in building these user-friendly wrappers around them. So this Wave2Vec2 has been around for a couple of years, and without these wrappers like Elpis around it, they will remain in the domain of being sophisticated speech science tools and never really get to the point of being beneficial to the ordinary working linguist. There are many more opportunities for wrapping existing tech. And one of the big potentials is around machine translation. And so again, translation being a language technology, which a lot of us are not going to take it for granted already through the interfaces provided by Google and Apple and such. But to think how these technologies might be useful for the rest of the world's languages through these similar approaches of co-designing wrapper technologies around existing algorithms. If you're interested in learning more about these approaches, in terms of learning the technologies, Google have some great online education resources for learning about machine learning. As this slide points out, they still can be quite heavy on the math. There are a couple of really good conferences for this in this space, and I'll just shout out particularly Computel and SLTU. They're very well worth looking at if you're interested in the development of language technologies, particularly around endangered and languages with limited quantities of resources. And there are some good books here about machine learning as well. And I should also shout out that University of Queensland has a Voyages in Language Technologies course, which covers a lot of these language technologies like speech recognition, text-to-speech, machine translation, sign language and gesture, and conversational AI and chatbots. If you're interested in finding out more about that, please get in touch, because all of that material will be online soon too.